All right, so we have a little bit more review with this video. We're going to talk about action potentials. And action potentials is really important because that's how neurons send signals, right? And so I just want to make sure that we understand this. Again, I know we reviewed it a little bit during week 1, but I want to make sure that that you guys understand what is going on. So just a couple of objectives. And again, these slides are for the most part the same as what I used in 220, but I just want to make sure we understand. So 3 stages of an action potential. Okay, and right here where I'm putting this green line, that's resting potential. So it's not really a phase of an action potential, but it's a very important one, right? And that's what we talked about. That's what we talked about last time. So just a reminder. Whoops, sorry, clicked the wrong button. So just a reminder, resting potential is an equilibrium point based on 4 different things. So our sodium influx from leak channels makes membrane potential less negative, and then everything else, potassium efflux through leak channels, the pump, and proteins make it more negative. So while the membrane potential is constant, remember that sodium and potassium are constantly moving in for sodium, out for potassium, but the pump is basically counteracting that, and that's establishing that negative 70 resting potential. Okay, when we're at resting potential, and really with an action potential, there are 3 different gates that we are concerned about. Okay, and so we have the sodium activation gates, which are closed, but the sodium inactivation gates are open. And so just a reminder, here's my cell membrane, okay? And then what we've got is this is my sodium channel right here, but there's 2 doors, okay? And we're just going to say this is inactivation and this is activation. In order for sodium to come into the cell, both of those doors have to open. But at resting potential, only one of them's open, so sodium can't go through. Now remember, we've got the leak channels, so sodium's still going through the leak channels, but it limits it, right? Because there's only so many leak channels. Then we've also got an additional gate, a voltage gate, which is a potassium gate, which is also closed, but it's just got a single door. So if that gate's open, potassium can go out. If it's closed, potassium can't go through it. But the leak channels are always open. Okay, and this is where when we're at that equilibrium point, we're at negative 70. So in order to go from resting potential to threshold, something has to happen. And whenever anything happens with a neuron that affects membrane potential, we're changing the cell membrane. Remember, cell membrane is one of the core concepts. And in order for a cell to do anything, we're messing with the cell membrane. And really what's happening is we're opening or closing doors. And so something's going to happen, whether that's let's just say we open a calcium channel and calcium goes into the cell. That is something that could cause our membrane potential to go from negative 70 to negative 55. Once we get to that negative 55, that's where all the fun stuff happens. Because these gates open, ions move. Okay? If we reach negative 55, that action potential will occur. There's nothing we can do to stop it. Once it goes, it goes. It's kind of like the all or none principle. Not kind of, it is. Either you have an action potential or you don't. And that's tied into muscle contraction too. If your muscle has an action potential, you'll have contraction. All right? And so as long as we reach this negative 55, we will have an action potential, okay? So we have to get from negative 70 to negative 55. When we hit negative 55, 2 things happen. One, and the primary one, is that the sodium activation gate opens, and it opens immediately. And so this allows a whole bunch of sodium to go into the cell. We've changed the system. There are thousands of sodium molecules trying to get into the cell, but there isn't enough openings for that all to get in. Now we've opened more doors so we can get in even more, or they can get in even more quickly. The other thing that happens, and it's kind of a big deal, kind of not, is that the potassium channel opens, but it opens very slowly. Okay? And so potassium can leave the cell, but it can't do it quickly. And so as a result, membrane potential becomes less negative. That's what depolarization means. Less, negative. D, less, polarization, negative. And so as a result, we have a stimulus, which basically allows for a whole bunch of sodium to go in. This is a positive feedback loop. Now, when we get to the top, and so just to be clear here, let me try and draw this. So we're to about here, okay? And we're going to say this is threshold. That line represents threshold. This one is rest. Okay, so from here to here, that is depolarization. All right. Now, when we get to the top, so right up here, we have repolarization. We go back down, and we're going to say this is my threshold. This is repolarization from this point back to this point, which is negative 70. So from plus 30 to negative 70, we're returning to our negative state. And that's polarization, negative. Okay, and what happens is we inactivate the action potential. In other words, the inactivation gate closes. And so sodium is no longer able to rush into the cell like it was before. But a reminder, leak channels are still opening, so some is going in, but not as much as what was going in during depolarization. The potassium gate continues to open. It's about halfway where it's fully open. So now we're allowing a lot of potassium out of the cell, and that causes us to return to our negative state. We have potassium efflux. So depolarization is due to sodium influx. Potassium efflux is what causes repolarization. All right, and so now here's threshold. We're going to say here is resting potential. And so we're going from here to here on the curve, okay? And so just in case some of you are confused, so my action potential looks something like this, right? And so I'm just talking about from here to here. When we get down to resting potential, everything resets like it was at rest. So inactivation is open, activation is closed, potassium gates close, or at least they start to close. Remember, they're slow. So as a result, as that potassium door is closing, potassium's still able to leave. Okay, until it's fully closed, potassium leaves. And so that potassium gate isn't fully closed until we get to about negative 85. Okay. And so from negative 70 to negative 85, we're becoming more, or hyper, polarized, more negative than normal. All right, and then the last thing is we've got to get back up to resting potential. We have to get from negative 85 to negative 70. And this is occurring because potassium is going back into the cell through the leak channels. Okay, there's still a lot more potassium inside the cell than outside. But what's happened is so much positive charge has left the cell and it's hanging out outside that you've got all these proteins that want positive charge. Remember, proteins are negatively charged. Proteins are basically calling the potassium ions back in. And so because there's actually a lot more potassium leak channels and sodium leak channels, this is due primarily, returning back to rest is due primarily to the potassium leak, potassium going back into the cell through the leak channels. Nothing happens with the gates except for these gates are fully closed. We get back to rest, and then the neuron waits until a stimulus causes it to get from negative 70 back up to negative 55.